So what is an identity? Now we know what equations are. So if we write, for instance, an equation, let's say we write, get some space here. Suppose we have this equation. Suppose we write x minus 7 is equal to 4. Now this is an equation and it is true for only a particular value of x. This of course is true if x is equal to 11. So it is an equation. If we have x squared minus say x plus x squared minus x minus, let me change it here, making up a number here, x squared minus x minus 2 equals 0. This is a quadratic equation and it would basically be true for at most two values of x. So equations may be true depending on the particular value of the particular variable. So if we were to factorize this would give me x minus 2, x plus 1 equal to 0, which would therefore mean that x is equal to 2 or x is equal to negative 1. So these are equations, and these equations can be true depending on the particular value of the particular variable. So if we write, for instance, if we write sine theta is equal to 1, this equation is true for a certain value of theta. It will be true for theta is equal to pi over 2 or 90 degrees. And if we were to write, for instance, cos theta is equal to 0.5, well, not degrees, but 0.5. Cos theta equals 0.5. Then this would be true if theta is equal to, say, 60 degrees, which is pi over 3, or also true if theta is equal to 300 degrees, which of course is, what is this now in terms of pi? That's what, 5 pi over 6, right? 5 pi over 6. So we should become familiar with angles in radian measure. So these equations are true for certain values of the variable. And so they are not what we call identities. Now, what exactly is an identity? An identity is a statement that is true regardless of the value of x or the variable that we put into it. So for instance, if we write down sine squared theta plus cos squared theta equivalent to 1, notice that we're not just using an equal sign, but a sign with 3 strokes. That is equivalent to. So this means is equivalent to. And that is a sign we use when dealing with identities. So once again, what is an identity? An identity is a statement that is always true for, let's say, all values of the variable involved. So if you write down sine squared theta plus cos squared theta is equivalent to 1, for any angle you can actually think of, when you find the sine of the angle and square it, find the cosine of the angle and square it, and then add those two, the answer is always going to be equal to 1. So I could pick an angle at random, sine of, say, 30 degrees squared plus cos of 30 degrees squared. That will give me 1. I could say sine of 50 degrees squared plus cos of 50 degrees also squared. That is also going to equal to 1, right? Somebody pick an angle, anybody pick an angle.
35 degrees.
35 degrees. If I put 35 degrees into this equation, I say sine of 35 degrees squared plus cos of 35 degrees also squared. This is equal to 1. And so that is why this is called a trig identity, because it is true for any particular value of the angle theta. So when we speak about an identity, we're talking about an expression which is always true for any value of the variable involved. Is that clear?
Yes, sir.
Right. I think what's her name? Is it Ty? This would be a first class Ty. Is it Ty? Miss Brown?
Yes, sir.
Right. So we're looking at trig identities. We'd have looked at a few stuff before, and the recordings, of course, are in the Google Classroom. So you could access the recordings from when we started the class. When was it, Anaki? Was it in late October, early October, or late September?
I think it's early October.
Right, early October. So we've been having the classes since early October. So we haven't done a lot, but I mean, the aim, of course, is to fulfill the entire syllabus between now and the exam time. So you're pretty much well prepared for the exams, right? So yes. So this is a new topic we're looking at today, trig identities, but it will probably involve some prior knowledge of trigs and trig functions. But of course, I will always try to introduce that knowledge that you may need to have. Right? So as I said before, this is one example of an identity, and it is one that people should be able to use, and of course, they want us to be able to prove it as well. Now, when proving it, I'm going to be using, let me use a little right angle triangle to prove that identity. So let me draw a right angle triangle here, or something resembling a right angle triangle. Right, come out so. All right, so let's imagine that this is a right angle triangle, okay? I'm going to call my angles, let me call my angles A, B, and C. So let this be angle A. I'm going to let this one be angle B. And, oh, well, the right angle is, of course, a 90-degree angle. So the corresponding sides, I'm going to let be the small letters. So where's my cursor? So let this be side A, and this, of course, be side B, right? And let my hypotenuse be C, right? So let my hypotenuse be C. So let's focus on angle A. If we're talking about angle A, then side A is the opposite, and side B is the adjacent, and of course side C is the hypotenuse. Does everybody see that?
Yes, sir.
So by definition, if we're talking about a particular angle, the angle, or the side rather, which is directly facing that angle is the opposite. So if I'm talking about angle A, then side A is my opposite, and of course side B is my adjacent, and side C is my hypotenuse. So I could say, for instance, sine of angle A is equal to opposite over hypotenuse. And therefore this would be equal to A over C, right? Also, I could say that cos of angle A is equal to adjacent over hypotenuse, and this gives me B over C. I could do for tan as well. I could therefore say that tan A is equal to opposite divided by adjacent, and this would be equal to A over B. So there I have my three major trig ratios. So I have my three major trig ratios. And of course, since I have these, I could actually write down the minor trig ratios as well. So you're required to have knowledge of the minor trig ratios. And those, of course, are cosec, sec, and cot. So what this basically mean is that cosec A, which is equal to 1 over sine A, this, of course, would be equal to C over A. Similarly, sec A, which is short for secant, sec A is equivalent to 1 over cos A, which would therefore be equal to C over B. And of course, cot A, which is equivalent to 1 over tan A, would be equal to B over A. So I just decided to write down those minor trig ratios as well, since we're in the habit of looking at those angles, right? Trig ratios. So now let's do something here. If I take sine A and divide it by cos A, what is that going to give me? Let me check. So if I take sine A and I divide it by cos A, then that gives me A over C divided by B over C. And of course, that gives A over C times C over B. When dividing fractions, of course, we reciprocate, or we flip or invert the second fraction, and we change the sign to a multiplication. So having done that, the two C's are going to cancel, and this leaves us with A over B. But what is equal to A over B? What do you notice there? A over B, what is that equal to? This is what? Tan A. So therefore, what this actually shows is that we can say that sine A over cos A is actually equal to tan A. And while this is just one right angle triangle, which we actually use to prove it, it remains true. So therefore, this, of course, is essentially our first trig identity. The sine of angle A divided by the cosine of the angle A is equal to the tangent of the angle. So for any angle where it is actually defined, the sine of the angle divided by the cosine of the angle is equal to the tangent of the angle. And basically, that is our first trig identity. All right, so that's our first trig identity. Now, here I use an equal sign, but generally, because we're talking about an identity, we can say that sine theta divided by cos theta is equivalent to tan of theta. Right? So that's basically our first identity. Now, let's go back our little right angle triangle. Right? Now, from Pythagoras' theorem, can anybody state Pythagoras' theorem for me, please? Anybody? Can you state Pythagoras' theorem?
A squared plus B squared equals C squared.
So A squared plus B squared equals C squared. So what happens if I actually label these sides with change around the letters? If this is A and this is, say, C, does Pythagoras' theorem still state that A squared plus B squared is equal to C squared? Would it hold for those sides if I change them around like that?
No, sir.
No. So that is why you probably should not practice to say Pythagoras' theorem like this, because it assumes that C is always the hypotenuse. So it's just that because in most right angle triangles, the letters A, B, and C are commonly used, and students have become so accustomed to seeing these letters that they quote Pythagoras' theorem as A squared plus B squared equals C squared. Now, according to Pythagoras' theorem, in any right angle triangle, the square of the hypotenuse, which of course is the longest side, is equal to the sum of the squares of the other two sides. So that is basically what Pythagoras' theorem states. But again, because students have associated a right triangle with sides A, B, and C, they normally say that A squared plus B squared equals C squared. But as long as you know how to apply it, then that is all right. But you have to understand that it doesn't necessarily equate to this, especially if the letters are rearranged, right? So, but using this particular triangle, let me just take back off these letters here. So in this particular case, yes, A squared plus B squared is actually equal to C squared. Now, let me do something here. Now, if you recall, from this triangle, sine A is equal to A over C. So we can say that sine A is equal to A over C, which therefore means that sine squared A, which is equal to A over C, all squared, that is equal to A squared over C squared, right? Let me just make some space. Similarly, cos A is equal to A over B. Not A over B, adjacent over, cos is adjacent over hypotenuse, right? So is B over C. So cos A is equal to B over C, which means that cos squared A is equal to B squared over C squared. Now let's combine these. Sine squared A plus cos squared A will be equal to A squared over C squared plus B squared over C squared. So here we have a fraction, or two fractions rather, with the same denominator. So we can just keep the denominators and combine the numerators. And so this gives us A squared plus B squared over C squared. But of course, if we go back and look at Pythagoras' theorem, then according to Pythagoras' theorem and this right angle triangle, A squared plus B squared is actually equal to C squared. And so this basically gives us C squared divided by C squared, which is therefore equal to 1. And from this, we can say that sine squared A plus cos squared A is equal to 1, or we can say is equivalent to 1 due to the fact that Pythagoras' theorem is always going to be equal to true, always going to be true. So from here, we can see that sine squared A plus cos squared A is equivalent to 1. And this is not only true for this right angle triangle, but it's true for any angle A. And this right here essentially is our second identity. So we have two identities thus far. Sine theta over cos theta is equivalent to tan theta, or if you're using A, sine A over cos A is equivalent to tan A. And of course, sine squared A plus cos squared A is equivalent to 1, right? So those are our trig identities thus far. Now, I also did introduce the minor trig functions, namely cosec A. Where's the cursor? Where's the cursor? Still not bottom. So the minor trig functions cosec A, sec A, and cot A. And of course, we're going to show identities related to those ones as well. So let's take this identity that we just showed. So this same one here, sine squared A plus cos squared A is equivalent to 1. And for this now, we're going to divide through. So we're going to divide both sides. We're going to divide through by cos squared A first. So first we're going to divide through by cos squared A. And what does that give us? We get sine squared A over cos squared A plus cos squared A over cos squared A is equivalent to 1 over cos squared A. Everybody with me so far?
Yes, sir.
Now, when you divide cos squared A by itself, what does that give us?
1.
So this right here is plus 1. Now, what is sine A over cos A? What does that give us in terms of trigs?
Tan squared A.
Right, so sine over cos gives us tan, and therefore sine squared A over cos squared A gives us tan squared A. And if you go back up to our trig, minor trig functions, 1 over cos is equal to sec, which therefore means that 1 over cos squared A is equivalent to sec squared A. And this is another trig identity that will always go, you're always going to have to use. Well, for those of you who decide to go on to do pure maths at sixth form level. So tan squared A plus 1 is equivalent to sec squared A. So that is one identity there, right? Now, the syllabus does not require you to be able to prove this one, but I just derived it to show you where it came from. And it basically stems from this identity, sine squared A plus cos squared A is equivalent to 1. Now, let's go a little bit further now. And this time we're going to divide by through by sine squared A this time. So let's take the same equation, but we're going to divide through by sine squared A. So if we do that, we get sine squared A over sine squared A plus cos squared A over, sine squared A over sine squared A would be equivalent to 1 over sine squared A. And from there, we know that sine squared A divided by sine squared A is equivalent to 1. So the first term here is 1. This term is basically 1 over, well, cot is 1 over tan. But of course, tan is sine over cos. And therefore, cos over sine will be cot. You understand?
Yes, sir.
So let me jot that down. We say that sine A over cos A is equivalent to tan A. But cot A is 1 over tan A, which would therefore be equal to cos A over sine A. Right, that is where that comes in. And so therefore we say that 1 plus cot squared A, 1 over sine is equal to cosec, and therefore 1 over sine squared A is equal to cosec squared A. And this is another trig identity, which again, you don't need to prove, but you may need to use to prove other trig identities, right? So this, of course, will be equivalent to cosec squared A. So thus far, we have these identities. Let me jot them down. We have sine, I'm just going to use theta, well, instead of A, right? So we have sine theta over cos theta is equivalent to tan theta. We have sine squared theta plus cos squared theta is equivalent to 1. We have tan squared theta plus 1 is equivalent to sec squared theta. And we have 1 plus cot squared theta is equivalent to cosec squared theta. So we have those identities thus far. So in this first session, we'll of course introduce all the identities that you'll need to use, and then we use the first set of them to actually prove other identities. Now, let's look at what we call compound angle identities or compound angle formula. So compound angle identities, and I just write them down. Again, we're not required to prove these. So we can say sine of A plus or minus B is equivalent to sine A cos B plus or minus cos A sine B. The signs at the top go together. So the plus is at the top over here, and the plus is at the top on the right-hand side, right? So we're talking about the signs here. The signs at the top will go together for this. So what this basically means is that, essentially, sine A plus B is equivalent to sine A cos B plus cos A sine B. And similarly, sine of A minus B is equivalent to sine A cos B minus cos A sine B, right? The next one is where you have cos. So you have cos of A plus or minus B is equivalent to, or this one go again, is cos A cos B, and this is minus or plus sine A sine B. Again, the signs at the top go together. So the plus sign on the left-hand side goes to the minus sign on the right and vice versa. So we can write that cos of A plus B is equivalent to cos A cos B minus sine A sine B. And similarly, cos of A minus B is equivalent to cos A cos B plus sine A sine B, right? So those are two of the three compound angle identities that we need to use. The third one is in terms of tan, and the third one goes like this. Tan A plus or minus B is equivalent to tan A plus or minus tan B over 1 minus or plus tan A tan B. So in the numerator, well, the signs at the top go together, likewise in the denominator. So what that means is that the plus sign over here goes with the plus sign in the numerator and the minus sign in the denominator. And of course, the minus sign here goes with the minus sign in the numerator and the plus sign in the denominator. So if we were to just write out these the versions like we did the other two, we can write that tan of A plus B is equivalent to tan A plus tan B over 1 minus tan A tan B. And then, of course, if we simply replace the plus sign, let me not be lazy and just write it over. If we now say that basically tan of A minus B will be equivalent to tan A minus tan B over 1 plus tan A tan B. And there we have our compound angle identities, right? So we listed most of the identities that the syllabus requires us to either prove or to use. And we have one last set, and these are called the double angle identities or the double angle formula. And they, of course, come from the compound angle identity. So let me just look at these, and then we'll start using some of the more basic ones to prove some identities. So let's look at the double angle identities, which are also referred to as a double angle formula. All right, so the first one we look at is this one. Sine of A plus B is equivalent to sine A cos B plus cos A sine B. Now, what we say is that when now let me not write it there. So we have that, right? So we have that. Now, what happens when A is actually equal to B? If A is equal to B, then essentially this becomes sine of A plus A is equivalent to sine A cos A plus cos A sine A. We know that multiplication is commutative, and therefore sine A cos A, same thing as cos A sine A. And therefore the final version of this is that sine 2A is equivalent to 2 sine A cos A. And that is our double angle identity or double angle formula for sine. So having done that, I want you to follow similar steps and do this one. Cos of A plus B is equivalent to cos A cos B minus sine A sine B, right? So what are you going to say? You're going to say that when A equals B, and you proceed to make that substitution and obtain the final version. Try that for me. Stepping away for a minute. Are you trying this?
Yes, sir.
Okay. All right, you managed to get the double angle formula for cos?
Yes, sir.
All right, so let's look at this. So the by its very name, it's called a double angle formula, which basically means that it's twice the angle. So when A is equal to B, then basically this becomes cos of 2A, which is equivalent to cos A minus sine A, which of course is the same thing as cos squared A minus sine squared A. So this is the original form of the double angle formula for cosine. But there are two other versions that we often see. And how do we arrive at these two other versions? We have to take into consideration where our first identity that we proved. So we're going to say, recall that sine squared A plus cos squared A is equivalent to 1. And if that is the case, then this means that sine squared A is equivalent to 1 minus cos squared A, or we can say that cos squared A is equivalent to 1 minus sine squared A. So what we'll do is we'll substitute first for sine squared A into this double angle formula, and then for cos squared A, and we'll get two further versions of this trig identity. All right, let's do that. So in the first case now, where we're going to substitute sine squared A is equivalent to 1 minus cos squared A, then this basically becomes cos 2A is equivalent to cos squared A minus, put that in a bracket because it's 1 minus cos squared A. And so this gives us cos squared A minus 1 plus cos squared A, which therefore gives us 2 cos squared A minus 1. And this is the other version of that identity. Cos 2A is equivalent to 2 cos squared A minus 1, right? For the final version, we will substitute for cos squared A instead. And when we do that, this is what we get. We get that cos 2A is equivalent to 1 minus sine squared A minus sine squared A. And this therefore gives us that cos 2A is equivalent to 1 minus 2 sine squared A. And this is the third version of that identity. So depending on the situation, we may need to use the first one, the second one, or the third one. With practice, you'll know when to use which, right? So we have one last double angle formula to look at, and that is in terms of tan. So once again, we start off with the compound angle identity. I have to make sure I don't bite my tongue. So we have tan of A plus B is equivalent to tan A plus tan B over 1 minus tan A tan B. And so therefore, when A equals B, what we get is tan 2A is equal to tan A plus tan A over 1 minus tan A tan A. We can simplify that, and so we get tan 2A is equivalent to 2 tan A over 1 minus tan squared A. Hold on. Am I missing a number here? Let me check something. Yeah, that should be it. That should be it.
Okay, sir.
Yes. So that takes care of our identities that we need to be able to use at this level, right? So with that in mind, we're gonna go back now and look at proving some identities. But of course, we're gonna focus on the first set that we looked at first, like these right here. And probably even more so the first two than the others, right? So sine theta over cos theta equals tan, sine square theta plus cos square theta equivalent to 1. Well, the others as well, definitely the others. Tan square theta plus 1 equivalent to sec square theta, and 1 plus cot square theta is equivalent to cosec square theta. So jot these down, right? If you haven't jot them down so that when you come to using them, you have them to look at, all right?
Sir, finish writing it down.
Okay, good. All right, so let's scroll up. I already had put a document in this with some questions to prove our identities, right? It's not solve equations, but prove. All right, so here we have the first set of identities that we're going to be proving. Let me just clear up the screen a little bit so I have some space to write. So when proving an identity, one of the first questions that we must ask ourselves is, which of the two sides is the more complicated? And we tend to start with the more complicated side and then try to break it down to make it look like exactly the other side. Now, sometimes that works and we can prove the identity rather having just manipulated one side. But in some cases, we have no other option but to manipulate both sides until you get both of them looking like the exact same thing. And you'll see exactly what I mean in a short while. So, all right, so let's look at the first one here. Can everybody see my screen clearly?
Yes, sir.
All right, let's start with number 1. So we're required to prove, so we can say RTP required to prove that sine theta, cot theta is equivalent to cos theta. Now look at that identity and tell me which of the two sides appears to be the more complicated of the two, the left side or the right-hand side?
The left one?
The left one, because the right side is just cosine. There's no way we can actually simplify cos theta to give any other simpler trig identity. So if it's just sine, cosine by itself, then that is going to be the simpler side. So for that reason, we're going to start with the left-hand side. So we say the left-hand side, LHS, is equal to sine theta, cot theta. Now, sine theta is a simple trig function, but the cot theta part, that is the more complicated part of this side. And if you remember, you must recall that cot theta is actually equivalent to cos theta over sine theta, right? Because cot is 1 over tan, and tan is sine over cos, and therefore cot is cos over sine. Is that clear?
Yes, sir.
Right? So LHS is therefore equal to sine theta times cos theta over sine theta. These will obviously cancel, which leaves just cos theta, which of course is equal to the right-hand side. And some mathematicians put a little Latin expression QED, which says that it is not proven, or they may put just a little box to show that you've proven what you've set out to prove. The Latin expression QED literally translates to that which we set out to prove, something so, right? So yes. So usually at the end of the identity, you put a little box or QED to show that you've proven the identity. All right? Give me 1 second.
Okay, sir.
Excuse me, sir.
Yeah, I'm back.
Could you go over this again?
No problem.
Yes, sir.
So we're required to prove that sine theta, cot theta is equivalent to cosine theta. So the first thing we try to identify is which of the two sides is or was the more complicated. And we generally agree that the left-hand side is the more complicated because it is a product of two trig ratios, sine theta and cot theta. And cot theta, of course, is one of the minor trig ratios. The right-hand side is just cosine theta. So there's no way we can actually make that any simpler, right? So as I said, we normally start with the more complicated side and simplify it. So there's no further simplification of cosine theta. So we had no choice but to start with the left-hand side. So we said that LHS is equal to sine theta cot theta. That is what it's actually equal to from the problem. But of course, we have to remember that cot theta, which is the reciprocal of tan, is actually equal to cosine theta over sine theta. So this right here, let me write it differently. So the LHS is simply equal to sine theta times cos theta over sine theta. So these two sine theta, of course, will cancel, leaving cos theta, which is exactly what the right-hand side is equal to. And in those few steps, we've proven our first identity, right?
Yes, sir.
Now, some of these will be a bit challenging, but it will get better with practice. I'll be honest with you. I mean, when I was doing identities for the first time I actually never did add maths in school. I did A-level maths, but I never did add maths. I used to struggle with these. A lot of things I actually used to struggle with until I actually decided to start teaching them. I had to sit down and teach myself these things and understand and make trial and error and multiple mistakes. And then eventually I start to figure out stuff. So sometimes, having done so many of these problems, you remember that you did something that looks vaguely familiar, and you remember what you did. So it will get better with practice. All right. So let's look at the second one. So number 2. So number 2 says that we want to prove, so RTP, that 1 plus tan squared theta times cos squared theta is equivalent to 1. So that is what we are going to try to prove now. Now, in many cases, there are multiple approaches to a particular identity, even when working with the same side, right? I will look at the different approaches here. So let's look at this first one. Now, clearly, the left-hand side is more complicated because on the right is just 1, right? So what do I do with this now? I could do one of two things. I will take different approaches. I could say that, for instance, we know that tan theta is equivalent to sine theta over cos theta, which therefore means that tan squared theta is equivalent to sine squared theta over cos squared theta. So having said that, I could say now that the LHS is equal to 1 plus sine squared theta over cos squared theta, and that is to be multiplied by cos squared theta, right? Now, if I carry out my multiplication, everything inside the bracket becomes multiplied by cos squared theta. And so my LHS becomes 1 times cos squared theta is cos squared theta. And then we have plus sine squared theta, cos squared theta over cos squared theta. And of course, the cos squared thetas would cancel. And so my left-hand side reduces to cos squared theta plus sine squared theta, which I know to be equivalent to 1. And therefore, my identity has been proven. Questions?
Can you go over the second part again, please?
When you say the second part, you mean which line? This line or this other line?
The second one, the LHS equal cos theta, cos square theta plus.
All right. So as we came to the right here and we established that tan theta is equivalent to sine theta over cos theta, right? This is from our trig identity. And therefore, if we have tan squared theta, then that must be equal to sine squared theta over cos squared theta, right? And so we replaced tan squared theta with sine squared theta over cos squared theta. Good?
Yes, sir.
Following?
Yes, sir.
And so what we're doing is we're multiplying the terms of this bracket by cos squared theta, which means that each term inside the bracket must be multiplied by cos squared theta. So I say cos squared theta times 1, that gives me cos squared theta. And then cos squared theta times sine squared theta over cos squared theta gives me sine squared theta, cos squared theta over cos squared theta. The cos squared thetas will cancel, leaving sine squared theta, and so the entire left-hand side basically becomes cos squared theta plus sine squared theta, which we know to be equivalent to 1 from our basic trig identity that we proved earlier with the right angle triangle. All right?
Yes, sir.
No, that is not the only approach you could have done for this one, but I think that would have been the simpler approach, to express tan in terms of sine and cos, and then simplify and then proceed. As a matter of fact, almost every trig identity can be proven by expressing all the trig ratios in terms of sine and cos. You should have realized now that every single trig ratio can be expressed as a combination of sine and slash or cosine. right? So for instance, tan is sine over cos. Cot is cos over sine. Sec is 1 over cos. And cosec is 1 over sine, and so on. So what I could have done here was to say this. So let me show you a slightly different approach. So I'm going to start with LHS one more time. So the LHS is equal to 1 plus tan squared theta times cos squared theta. But what do I remember? I remember that 1 plus tan squared theta is equivalent to sec squared theta. And so my LHS becomes sec squared theta times cos squared theta. But of course, what is sec theta? Sec theta is 1 over cos theta, which therefore means that sec squared theta is equivalent to 1 over cos squared theta. And so this basically gives us 1 over cos squared theta times cos squared theta, and put it over 1, which simply gives us 1. So here again, the identity has been proven, right?
Yes, sir.
Yeah. All right, so that was number 2. Let's look at number 3. Now, I know most of you have the black textbooks, which is what? We'll call it again. Add Maths for CSEC or CSEC Add Maths, that book.
Yes, sir.
Yes.
So is there anybody who does not have that book?
I have an online copy.
Oh, well, yeah, you still have a copy. Good. You have an online copy, as in the PDF version?
Yes, sir.
All right. I'm going to ask you to email it to me, okay?
Okay.
I've been wanting to get a copy of that book for quite some time. When I went to Trinidad in the summer, I was supposed to buy one, but I did not remember. So I really appreciate it. Just message me later because I can't identify you by the voice. Okay?
Okay, sir.
Sir, the book that
Yes.
I have is Additional Mathematics, a complete course for CSEC.
Repeat that, please.
The book that I have is Additional Mathematics, a complete course for CSEC.
That's by Raymond Tulsi.
Yes, sir.
Yeah, that's the book I'm talking about. Yes.
Okay.
I mean, Raymond Tulsi is the same author who has been who wrote those math books, CSEC math books that have been used from ever since long before I probably was at CSEC age. The green one and I think there's the green and yellow. One of them is now gray. Maths for CSEC. Yeah, he's the same author, and he has now written an Add Maths textbook, and he's also written a series of K pure maths textbooks. So for those who are looking to go into sixth form to the pure maths, then you'll be using either some of his books or some of books by Dipchan Bahal. Both of them are Trinidadians. So let's look at number 3. Number 3 says we want to prove, so we're required to prove RTP that bracket 1 plus tan squared theta times 1 minus sine squared theta is also equivalent to 1. Right? And most of these identities that you see is equivalent to 1, at least some of them. Anyways, let me not say that. Next thing I say anything wrong. All right, so we have 2 parts of the identity here. And again, once again, the left-hand side is clearly the complicated side. So what we can do is we can actually express each of these expressions in the brackets in terms of a single term. Can anybody tell me what 1 minus sine squared theta is equivalent to? Anybody remembers that? No? That's all right. So 1, remember that. Let me write it down. We know that sine squared theta plus cos squared theta is equivalent to 1. And this therefore means that cos squared theta is equivalent to 1 minus sine squared theta. So therefore, anywhere we see 1 minus sine squared theta, we could replace it with cos squared theta. Is that clear?
Yes, sir.
Yes, sir.
Similarly, we should also remember that 1 plus tan square theta is equivalent to sec square theta. So basically, this right-hand side, or the left-hand side rather, becomes sec square theta times cos square theta. And of course, even from the previous example or the previous question, we know sec square theta is 1 over cos square theta, and that times cos square theta, which is simply equal to 1. So our identity has been proven, right? So
Yes,
two
sir.
different people might take completely different approaches to proving the same identity. You don't get any extra marks if you take 20 steps and the other person took 2 or 3 steps. So the aim is not to make it as complicated as possible, it's to prove the identity. And if you can recognize that you can prove the identity in 2 or 3 steps, that is fine, you get your marks, okay? So knowledge of the basic identities is important because you'll have to use those identities when proving other identities. So you had to have remembered that, for instance, 1 minus sine square theta is equivalent to cos square theta, and 1 plus tan square theta is equivalent to sec square theta. But I will show you a different approach which will work, but it'll take us a few more steps. So let me do this part again. All right, let me start from scratch again with this one. So what I'm going to say is this. Should I do that part? Let me see. Yes, I will. All right. So watch this now. I would basically say that 1 plus tan square theta is the same thing as 1 plus sine square theta over cos square theta. Now I have this fraction sine square theta over cos square theta, and my other fraction is 1 over 1. So I could actually write the 1 as cos square theta over cos square theta, and this is plus sine square theta over cos square theta. Everybody seeing that?
Yes, sir.
So because I'm adding two fractions, I make my life a little bit easier by expressing both fractions to the common denominator, which happens to be cos squared theta. And so the denominators are the same. I could just add the numerators, which gives me cos squared theta plus sine squared theta all over cos squared theta, which of course is equal to 1 over cos squared theta. So that is just that little part of the left-hand side. And now I could actually say now, since I know that this as well, that this is true, then I could say that the LHS, once again, the LHS is equal to 1 over cos squared theta times cos squared theta, which is equivalent to 1. So slightly different approaches, but same end result, okay?
Yes, sir.
All right, so I think you should be able to do number 4. Try number 4. Number 4 says, prove that cos square theta minus sine square theta is equivalent to 1 minus 2 sine square theta. And I want to suggest that you will have to use some variation of this one. Sine square theta plus cos square theta is equivalent to 1. Now you must pay attention to both sides of the trig identity. If you notice on the left-hand side, we have cos squared theta and also sine squared theta, but on the right-hand side, we only have sine squared, which obviously says that we're going to have to make a substitution for cos squared theta, right? So go ahead and do that.
Sir, I'm finished.
Okay, good. Thanks, Dejani. I got your email.
No problem, sir.
But I don't understand why you declined the invitation to the session earlier, though. How was that by mistake?
I think that was an error.
Okay, no problem, no problem. All right, so this one was not a difficult one. It's pretty straightforward, to be honest. And well, let me not say, yeah, it should have been. Um, and I actually proved this one already when I was deriving double angle formula, right? So let me just go through that one. All right, so this one, we can see, we start with the left-hand side. Left-hand side is equal to cos squared theta minus sine squared theta. But from right over here, we see that cos squared theta is equivalent to 1 minus sine squared theta. So this, of course, is the same thing as 1 minus sine squared theta minus sine squared theta, which simply equals 1 minus 2 sine squared theta, right? Which, of course, is equal to the right-hand side. And so our identity has been proven. Okay?
Yes, sir.
All right, I want to try number 5, but what I will advise about number 5 is this. With number 5, now so far, all our identities that we've proven, we've been able to start with one side and then work until we got the other side. With number 5, you may need to actually work on both sides. So if you start with the left-hand side, you might not looking exactly like the right-hand side. You have to do some work with the right-hand side as well. I want you to try it first. And these are, let me write down the information that you might need. You may need to remember that sec theta is equivalent to 1 over cos theta. And of course, tan theta is equivalent to sine theta over cos theta. So you just may need these two. So start with whichever side. I would say start with the left-hand side. And after you realize it can't go any further, then start with the right-hand side. And ultimately, the two expressions should be the same. You understand?
Yes, sir.
Yeah, go ahead. Getting through?
Sir, get in there. Get in there.
Right, no problem. Try. The important thing is to try. That's right. All right, so it's time for me to intervene. If you're making progress, let's see. So as I mentioned, some of these identities, we're able to prove them by just working on one side, the more complicated of the two sides. But in some cases, we have no other option but to work on the two sides until we get an expression which is the same. So this might be one of those. So in number 5, let's start with the left-hand side. So I'm going to say that the left-hand side, LHS, is equal to sec theta minus cos theta. This I can write as 1 over sine theta minus cos theta over 1. Now, because I have two fractions here, I'm going to combine them to give a single fraction. So I'm going to draw a line under and write down my common denominator, which is sine theta. And I will say sine theta into itself. That goes once. 1 times 1 is 1. And then I will say minus 1 into sine theta is sine theta. Then we have sine theta times cos theta. So I don't see how much simpler I could actually make that. So I will leave that as it is, right? Let me go over now to the right-hand side and see what that gives me. Now for the right-hand side, I will use the fact that tan theta is equal to sine theta over cos theta. So my right-hand side, RHS, is equal to sine theta, tan theta, which of course is equal to sine theta times sine theta over cos theta. And this, of course, will give me sine squared theta over cos theta. Where do we go from here? So let me see, that is sine theta, tan theta, sine over cos, sine squared theta over cos squared over cos theta. So what I could probably do is make some space here. All right, I made a mistake. Sorry. I see a mistake. Let me fix this. I absolutely made a mistake here. Sec is 1 over cos, not 1 over sine. So let me fix that. So let me backtrack a bit. Yeah, let me backtrack. So sec is 1 over cosine, not 1 over sine. The s and the s don't go together. So let me fix back here. Let me go back here. So this is equal to 1 over cos theta, right, minus cos theta over 1. I will same approach with the fraction. The common denominator is, of course, cos theta. Cos theta into itself goes 1. 1 times 1 is 1. Hope at the minus sign. Then I say 1 into cos theta, that goes cos theta. Cos theta times cos theta is 1 minus cos squared theta. And of course, I know that 1 minus cos squared theta is equivalent to sine squared theta, and I have that over cos theta. No, I actually did not need to work on both sides, and I'll show you why. So both sides, the right-hand side is that, sine theta, tan theta. So if I examine this carefully, I should probably recognize that I could write this. I could write this as sine theta times sine theta over cos theta. And of course, by now we should know that sine theta over cos theta is equivalent to tan theta. And so this gives us sine theta, tan theta, which of course is equal to the right-hand side. Right? So my initial little mistake would have caused me to do a lot of what I did not need to do, but because of that little mistake. Did anybody get it out?
Yes, sir.
All right, good. So remember, the key is to keep trying. You won't always get them initially, but you have to keep trying. As I mentioned before, when I first started doing these problems years ago, I used to struggle. And it wasn't until I actually decided to start teaching add maths and teaching K-pure maths, I actually started to understand many things that I never understood at the high school level, right? And even beyond. So they always say that you don't fully understand something until you could actually explain it. Well, obviously in your case, you don't need to be able to explain it. You just need to be able to reproduce it, right? All right, so that was number 5. Number 6. So let's tackle number 6. And I'll probably just tell you what identity that you need to use, and you can actually go ahead and try number 6. So number 6 says, want to prove that cot square theta times 1 minus cos square theta is equivalent to cos squared theta. So once again, we're going to ask ourselves, which of the two sides appears to be the more complicated? Which of them appears to be the more complicated side?
On the left side.
Right, the left-hand side. So this is number 6. We're required to prove that cot squared theta times 1 minus cos squared theta is equivalent to cos squared theta. So if you're going to be working with the left-hand side, I'll just give you a few little clues. You need to remember that cot theta is equivalent to cos theta over sine theta, which therefore means that cot squared theta is equivalent to cos squared theta over sine squared theta. And it could also help, well, I won't tell you this one, but I will tell you that you will need to replace this with something else too. And you should know what that is going to be, right? So go ahead and try that one. So this one you should be able to do by just working from the left-hand side.
Finished, sir.
All right. Who was that? That was who?
Dijon Jonas.
Okay, I still have to get used to the name. Well, the voices, the voices. And I have a little AdMats WhatsApp group, I mean, it's not very active because people don't normally send messages asking for help with questions or anything like that. But let me see, what did I add recently? So if you have any question or any, you feel free to send it in the group. I mean, other students might benefit from if you have a question, others might actually have had similar questions, so it might help.
Noted, sir.
Mm-hmm.
Okay, sir.
All right, so let me tackle this one. So I gave you some hints, and so we could start with the left-hand side. We could say the left-hand side, since I told you what cot squared theta is equal to, this is going to be equal to cos squared theta over sine squared theta times. Now, I did put a little bracket under 1 minus cos squared theta, hinting that you need to change this, but you should have been able to figure out what to change it to, because we have this identity over here. Sine squared theta plus cos squared theta is equivalent to 1, and therefore 1 minus cos squared theta is actually equivalent to sine squared theta. And you could put it over 1. And so when you multiply these through, then the sine squared theta here will cancel that. And all we're left with is cos squared theta. All right?
Yes, sir.
All right, that was number 6. Now let's try number 7. Now, number 7 says that we want to prove, so RTP, that 1 over cos squared theta minus 1 over cot squared theta is equivalent to 1. So once again, we're going to use the fact that cot squared theta is equal to cos squared theta. So I think, but of course it is, well, one of two things. Yeah, we could use that, but of course you could also use the fact that 1 over cot squared theta is equivalent to tan squared theta, and use the fact that tan is equal to sine over cos. So go ahead and try this one. 1 over cot squared theta is equivalent to tan squared theta, but of course you should remember that tan squared theta is equivalent to sine squared theta over cos squared theta. So try that one. And especially for those of you who have recently joined throughout the week, if you have any problem with the AdMaths question, feel free to message. I will always respond in a timely manner as I possibly can.
Okay, sir.
Hello? Getting through?
Yes, sir. Finished.
Okay. All right, so let me look at this one. That's number 7. We have 1 over cos squared theta minus 1 over cot squared theta equivalent to 1. So we identified that basically that 1 over cot squared theta is equivalent to tan squared theta. And of course, tan squared theta is equivalent to sine squared theta over cos squared theta. So we can therefore say that the left-hand side is equal to 1 over cos squared theta minus sine squared theta over cos squared theta. Here we have two fractions where the denominators are the same, and so we can just subtract the numerators. And so this becomes 1 minus sine squared theta over cos squared theta. And basically, from our trig identities, 1 minus sine squared theta is equivalent to cos squared theta, and that is divided by cos squared theta, which of course is equal to 1. All right, so that one is proven there. All right, so let's go through a few more. All right, number 9 looks a little bit complicated, but I want you to try number 8. So try number 8. Number 8 says required to prove or prove that cot theta divided by tan theta plus 1. So I'll give you a few little hints, all right, because so you can use those little hints to do that. So what you could do here, basically, we know that cot theta is sine theta over cos squared theta. And we know that tan theta is sine theta divided by cos theta. So you can divide those two fractions and simplify it as far as you possibly can. And if you need to work on the right-hand side, you may need to do that as well. So for number 8, you want to prove that cot theta over tan theta plus 1 is equivalent to cosec squared theta. So use the fact that cot theta is equivalent to cos theta over sine theta, and also that tan theta is equivalent to sine theta over cos theta. That is one approach, right? So you divide that fraction, add it to 1, and then simplify. Or you could simply say that, or you could say that, for instance, cot theta is equivalent to 1 over tan theta, and use that instead, and then simplify the right-hand side. So try either approach and see if you can do that one, okay?
Okay, sir.
Yes.
Getting through?
Yes,
Yes,
sir.
sir. Finished.
Should get to the right sushi right so. All right, so this one is not one of the longer ones. Though do this one. I'll do it the both ways I would have showed you. In case anybody tried either method, right? So let me use the first one. Let me use the second one first. All right, so I want to prove that cot theta over tan theta plus 1 is equivalent to cosec squared theta. But of course, I know that cot theta is equivalent to 1 over tan theta. So I could say that the LHS is equal to, it's the same thing as 1 over tan theta divided by tan theta plus 1, which of course is the same thing as 1 over tan squared theta plus 1. From our trig identities, well, 1 over tan will be equal to cot, and therefore 1 over tan squared theta is equal to cot squared theta plus 1, right? Which of course we do know to be equivalent to cosec squared theta from our list of identities. So that's that one there, proven. So we reduce the left-hand side to cot squared theta, which of course we know is equal to, well, cot squared theta plus 1, which we know is equal to cosec squared theta. And that one has been proven like that. Now, I also said that you could have written cot theta as cos theta over sine theta and tan theta as sine theta over cos theta. Let's take that approach as well. So there are usually different approaches of proving the same identity, and if either approach works, then I mean you're good to go, right? All right, so this case now we have the LHS is equal to cot theta divided by tan theta plus 1. Now, this is the same thing as cos theta over sine theta divided by sine theta over cos theta plus 1. When we divide fractions, we reciprocate or invert or flip the second fraction and change the sign from division to multiplication. So we get cos theta over sine theta times cos theta over sine theta plus 1. When you multiply that up, we get cos squared theta over sine squared theta plus 1, which of course is equal to cot squared theta plus 1, which we do know to be equal to cosec squared theta. So regardless of the approach, either approach gave the same result. The left-hand side are able to simplify to give cot squared theta plus 1, which we know to be equivalent to cosec squared theta. All right, so we're going a little bit beyond 5:30, but let's do another one or two from this. And of course, I will implore you to practice some questions from your textbook, right? Now that I actually have a copy of the textbook, I could assign questions. Yes. I could say go to this page and do those questions, practice them for homework, and so on, right? So yeah. Now that I have a copy of the book, I could do that. I hope Dejani don't regret sending me the book now, you know. All right, so look at number 10. So number 10 says we're required to prove, yeah, this one looks long. I to prove that sine theta plus cos theta times tan theta plus cot theta is equivalent to sec theta plus cosec theta. So this one is long. So I'll work through this one. Now, let's look at the left-hand side. Again, the left-hand side is, as is often the case, the more complicated of the two sides. So I'll start with the left-hand side. So I'll say my LHS is equal to sine theta plus cos theta times tan theta plus cot theta. Now, clearly, the first bracket of the left-hand side can't be simplified any further. So that can't be simplified any further. So we have to simplify this second bracket. So let me just write out the term. So I could say that tan theta plus cot theta is same thing as cos theta over sine theta plus sine theta over cos theta. Now, should I go any further with that? I think I could go a little bit further, yes. So I will draw a line underneath for my common denominator, which is sine theta cos theta. Then I will say sine theta into sine theta cos theta. That leaves cos theta, right? So I will divide sine theta, which is the denominator of this fraction here, into this. That will leave cos theta, and then I will say cos theta times cos theta gives me cos squared theta. Similarly, I would say cos theta into this fraction here. The cos thetas will cancel, leaving sine theta, and then sine theta times sine theta is sine squared theta. And once again, here we see cos squared theta plus sine squared theta, which we know is going to be equal to what? What value would the numerator be equal to?
Sir, 1.
1. Because for any angle theta, cos squared theta plus sine squared theta is equal to 1. So this gives me 1 over sine theta cos theta. So that is just a second bracket. So I could go back and say now that the LHS is equal to sine theta plus cos theta times 1 over so this is times 1 over sine theta cos theta. So I missed the plus sign is there. So right. So multiplying out that, I could basically get that we have sine theta over sine theta cos theta plus cos theta over sine theta cos theta. So from the first bracket, or for the first term, sine theta will cancel the sine theta, and from the second, cos theta cancels the cos theta, and so what I'm left with is 1 over cos theta plus 1 over sine theta. So this gives me 1 over cos theta plus 1 over sine theta, which of course I know to be sec theta plus cosec theta. And I think that is what was on the left-hand side, right-hand side, yes. So that is equal to sec theta plus cosec theta, and therefore I have proven my trig identity. All right? So we have gone through the identities that the syllabus requires you to be able to use. Well, not only use, but required to be able to derive as well. And we'd have used many of those to actually prove other identities. So we're going to be continuing with that next week. And probably most likely we'll be able to wrap up trig identities next week. Look at some past paper questions, and the following week start module 3. All right? Any questions before? Right, so I'm just seeing Dejane's message that she has to leave. Okay, that's fine. All right, so yes, any questions before the rest of us leave?
No, sir.
All right, so take care. And of course, once again, I'll implore you to work diligently on your SBAs, finish your SBAs, submit them as quickly as possible for them to be marked and uploaded. And of course, don't neglect the fact that you have exams in about 3 months' time. I mean, some of you might have exams before, depending on the subjects that you do. If you do anything like food and nutrition or PE or those subjects with those kind of practicals, or the orals for the languages might come a little bit early. So, right? So try to be as diligent as possible. Leave out the TikTok, leave out the IG and the Snapchat, and focus on your schoolwork. Around July, you could always pick up back those things after exams finish. All right?
Yes, sir.
Okay, sir.
All right, take care. I'll see you all again next week.
Same
Bye,
to you,
sir.
sir.
Bye, sir.
Bye.